Welcome to our deep dive, and today we're tackling a real head-scratcher in cosmology.
Oh, yeah.
It's called the Hubble tension. And basically, imagine trying to measure a room with two different rulers,
Okay.
but they keep giving you different answers. That's kind of the problem we're facing when we try to figure out how fast our universe is expanding.
Oh,
We've
yeah.
got these two super reliable methods, but they just don't agree.
Interesting.
So to help us make sense of all this, we'll be diving deep into a Scientific American article
Okay.
and some recent research excerpts.
Great.
Are you ready to explore the mysteries of this expanding universe?
Absolutely.
And maybe even bump into something called early dark energy along the way?
This tension really highlights how much we still don't know about the universe.
Yeah.
Like, we have this model, the standard model of cosmology.
Right.
And it's been super successful at explaining so much of what we observe out there.
Mm.
But this discrepancy in the expansion rate, this Hubble tension, that's what we're calling it, it kind of suggests that there might be something fundamental, that we're missing something big. Maybe even some new physics that we haven't even thought of yet.
So let's break this down a bit. We're talking about the expansion of the universe,
Right.
Right? Like, imagine dots on a balloon.
Yeah.
As you blow it up, the dots get farther apart.
Exactly.
But we're talking on a cosmic scale here.
Exactly. On a cosmic scale.
And the Hubble constant, that's like our speedometer.
Yeah.
It tells us how fast those galaxies are moving away from each other.
Exactly. That's our measure of how quickly space itself is stretching.
So this term Hubble tension, it's not exactly a new kid on the block in cosmology, right?
No, you're right. That's
Yeah.
popped up a couple of times over the years. And each time it's led to a pretty big shift in how we understand the universe.
Really?
The first time was way back after Edwin Hubble's discovery.
Oh, so we're talking 1920s.
Yeah, 1929. He observed that galaxies are moving away from us, which was huge. It was proof that the universe is expanding.
So that's how we know the universe isn't static, but is actually stretching out in all directions.
Precisely. It's not just sitting there. It's dynamic.
Yeah.
It's evolving.
Okay, so you said there was a problem with Hubble's initial calculations, though, right?
Well, yeah, his initial calculation for this Hubble constant, it implied a universe that was younger than our own solar system.
Oh, that's a bit of a problem.
Yeah, just a tad.
Well,
Clearly something wasn't quite right.
yeah.
Turned out the distances to the galaxies that Hubble was using were underestimated.
Oh, I see.
So that skewed his results.
So that first tension got resolved, but then you said in the 1990s a new one popped up.
Yeah, a new tension emerged. And this one is even more interesting.
More interesting. Okay, so what happened in the 90s? Did our measurement techniques get better or something?
Much better. We had the Hubble Space Telescope by then.
Of course.
And with Hubble, we could get way more precise measurements.
Gotcha.
And the data, it revealed something completely unexpected. The expansion of the universe, it wasn't just happening, it was accelerating.
Hold on, so an already expanding universe is expanding even faster.
Yeah, it's like hitting the gas pedal on the universe's expansion.
And this is where dark energy comes into the picture, right? This mysterious force pushing everything apart.
Exactly. Dark energy is our placeholder for whatever is causing this accelerated expansion.
Okay, so we've got this accelerating expansion fueled by dark energy, and now we're saying that the two best ways we have to measure this expansion.
They don't agree.
Don't agree. Okay, let's dive into these cosmic rulers, as we called them earlier. How do they actually work?
All right, so one method, the cosmic distance ladder, it's like building a staircase to measure those vast distances to galaxies.
A staircase. Okay.
To do this, astronomers use objects with a known brightness called standard candles as their measuring stick.
So it's like if you know how bright a light bulb is supposed to be,
Right.
you can tell how far away it is based on how dim it appears.
Exactly. It's all about relating brightness to distance.
And there's a specific type of star that's super useful for this, right?
Yes. Cepheid variable stars. They pulsate.
They what?
They pulsate with a rhythm. And that rhythm is directly tied to their actual brightness.
Really?
It's like a cosmic heartbeat that tells us how much light they're pumping out.
Huh. And who figured this out?
That was Henrietta Swan-Leavitt back in the early 1900s.
Wow.
Her discovery was revolutionary. It changed our ability to measure those massive cosmic distances. Before her, it was like trying to navigate the universe without a map.
So by observing these Cepheid variables and knowing their true brightness, astronomers can calculate how far away they are.
That's the idea. It's one of the key rungs on our cosmic distance ladder.
The article also mentions something called a parallax ladder.
Oh, yeah.
What's that about?
Okay, so think about holding your finger in front of your face and close one eye, then the other.
Okay.
Notice how your finger seems to jump back and forth.
Yeah.
That's parallax.
Okay.
Astronomers use the same principle, but on a cosmic scale, to measure the distance to nearby stars.
So it's like using a smaller, more accurate ruler to calibrate a larger one.
Exactly. And these measurements then become the foundation for calibrating those distances to the more distant Cepheid variables.
So that's our first method, the cosmic distance ladder, with a little help from Henrietta Swan-Leavitt.
That's right. It's our way of using known objects to step our way out to those far-off galaxies.
Okay, what about the second method? This one seems even more mind-blowing.
All right, this one takes us all the way back to the very beginning, to the afterglow of the Big Bang.
Wow.
It's called the cosmic microwave background, or CMB. It's a faint signal from when the universe was just a baby.
A baby picture of the universe?
Yeah.
That's wild. How can we get the expansion rate from something that happened billions of years ago?
Okay, so imagine sound waves rippling through the early universe.
Okay.
The sound horizon is the distance those waves could travel before the universe cooled down enough for atoms to form.
So we're basically looking at the size of these variations in this baby picture of the universe.
Essentially.
Yeah.
And from that, we can figure out the sound horizon.
Gotcha.
And that tells us the expansion rate at that very early time.
So this CMB method gives us our second measurement for the Hubble constant.
Right. And based on incredibly precise measurements from satellites like WNAP and Planck, the CMB method suggests a Hubble constant of about 67.5 kilometers per second per megaparsec.
Okay, but here's the kicker. The distance ladder method, the one using Cepheid variables and supernovae, that gives us a value of around 73 kilometers per second per megaparsec.
That's the tension.
That's a pretty significant difference.
It is.
So what's the deal? Are we just unlucky? Is the universe playing some cosmic joke on us?
Well, that's the million-dollar question. That's what makes this Hubble tension so fascinating.
Yeah.
Some scientists think it could just be systematic errors in our measurements.
Okay.
But others propose it might be a sign of new physics, something we haven't even considered yet. And one of the most intriguing ideas is the idea of early dark energy.
Okay, early dark energy. Now we're talking. So how does this idea fit into all of this?
Well, the standard model of cosmology assumes that dark energy has been a constant force throughout the universe's entire history. But what if that's wrong? What if in the early universe, dark energy was much stronger?
So you're saying dark energy might have had a much more dramatic role to play in the early universe than we initially thought.
That's the idea. And that could potentially explain this discrepancy in our measurements. It could have really shaken things up in the early universe and then settled down over time.
Okay, so early dark energy, maybe it's the missing piece that explains why our measurements of the universe's expansion rate are kind of all over the place.
Yeah, that's one possibility. It could help bridge the gap between those two conflicting measurements.
But the article mentioned there are like two different ways this early dark energy might have behaved.
Right.
Can you break those down for me?
Sure. So one idea is that this early dark energy might have been what we call a slowly rolling scalar field. Imagine a ball rolling down a hill.
Okay.
The ball starts with a lot of potential energy, but as it rolls downhill, it loses energy and slows down.
Okay, I'm with you.
Similarly, this scalar field would have started with a ton of energy in the early universe and then gradually just kind of decayed away, leaving us with the much weaker dark energy we see today.
So it's like the universe had this extra burst of energy early on and then it kind of fizzled out.
Exactly. It's a smooth transition from high energy to low energy.
Okay. What about the second idea?
The second possibility is a rapidly oscillating field. Think of a pendulum swinging back and forth,
Okay.
constantly converting between potential and kinetic energy.
Got it.
Now imagine that happening on a cosmic scale, with this energy field rapidly oscillating in the early universe.
So instead of gradually fading away like that ball rolling down a hill, this energy field would have been much more dynamic, constantly fluctuating.
Exactly.
What kind of impact would that have had?
Well, this rapid oscillation, it could have had some pretty wild consequences.
Like what?
For one, it could have messed with the formation of galaxies and other large-scale structures in the universe.
Really?
Yeah, and it might even give us some clues about particle physics,
Oh, interesting.
potentially pointing towards the existence of new particles, or even new forces that we don't know about yet.
So this is getting into some pretty mind-bending stuff.
It is. We're talking about potentially rewriting our understanding of the universe.
Okay, but hold on. Didn't the article say that recent data from the Atacama Cosmology Telescope, ACT, they call it,
Yes.
that data seemed to challenge this whole early dark energy idea?
Well, the ACT data does seem to favor the standard model of cosmology, which doesn't include early dark energy, but it doesn't completely rule it out.
So there's still a chance.
Absolutely. Remember, science is all about ongoing investigation.
Right.
It's like piecing together a giant jigsaw puzzle. We get a new piece of information, and we got to see how it fits with everything else.
Right.
Sometimes we have to adjust our understanding, try different approaches, even go back and look at pieces we thought were already in place.
So the ACT data, it's just one piece of the puzzle.
Exactly. It's a valuable piece, but it's not the whole picture.
So we still need more evidence, more observations to figure out what's really going on.
We need more data to see if early dark energy truly fits, or if we need to explore other explanations.
What are some of the other things scientists are considering to explain this whole Hubble tension thing?
Well, one approach is to double-check our existing methods, especially that cosmic distance ladder.
Right. Making sure our measurements are accurate.
Exactly. Scientists are looking at the measurements of those Cepheid variables and supernovae with a fine-tooth comb, trying to find any possible sources of error or bias. Even tiny uncertainties in those measurements can have a big impact on those calculations of the Hubble constant.
So it's like double-checking our math, making sure we didn't miss a decimal point or something.
Exactly. We need to be as precise as possible.
What about the CMB data? Are scientists looking at that in different ways?
Absolutely. Some scientists are wondering if maybe our understanding of the physics of the early universe needs some tweaking.
Tweaking?
Yeah, like maybe there are processes we haven't fully accounted for that could affect that sound horizon.
Oh, I see.
And that would obviously impact our interpretation of the CMB data.
So we might need to adjust our assumptions about how the early universe worked.
It's a possibility. We're constantly learning and refining our understanding.
This is like peeling back the layers of a cosmic onion.
I like that analogy.
Each layer reveals something new and challenges our preconceived notions.
Exactly. That's what makes cosmology so exciting.
Okay, but what about some really out there ideas? Are there any really wild theories scientists are throwing around?
Well, one area that's getting a lot of attention is modified gravity.
Modified gravity. Now that sounds like science fiction.
It might sound far out, but remember, the idea of dark energy itself was considered pretty radical at first.
That's true.
The universe has a way of surprising us, and we got to be open to new possibilities, even if they seem strange or challenge our current understanding.
So modified gravity, what does that even mean?
It suggests that Einstein's theory of general relativity, which describes gravity as we know it, might need some adjustments.
Adjustments to Einstein. Now that's a big one.
It is, but it's not entirely out of the question.
Yeah.
Especially at those vast cosmic scales or under the extreme conditions of the very early universe.
So maybe gravity doesn't work exactly the way we thought it did, especially on those massive cosmic scales.
That's what some physicists are proposing.
It's like we need to rewrite the rules of the game.
Maybe just tweak them a little bit.
But the point is, we have to keep an open mind and be willing to explore different ideas.
Absolutely. We can't be afraid to challenge our assumptions and follow the evidence wherever it leads.
So with all these different theories and ideas floating around, what are the next steps in this whole cosmic detective story?
That's a great question.
What kind of experiments or observations could help us get closer to the truth? So we've been talking about this whole cosmic puzzle, this Hubble tension thing.
Right.
And how scientists are trying to figure out why these different ways of measuring the universe's expansion rate give us different answers.
Yeah, it's a real head scratcher.
It's like trying to solve a mystery where the clues just don't add up. But I'm curious, what are the bigger implications of this? Does it change our understanding of the universe in some big way?
Well, it definitely raises some really profound questions about the universe.
Like what?
Well, one of the most fundamental questions is about the age of the universe.
Oh, okay.
The Hubble constant. It's key to figuring out how long ago the Big Bang happened.
So if we have two different values for the Hubble constant, it's like having two different guesses for how old the universe is?
Precisely.
Hold on. Are you saying our universe might be younger than we thought?
Well, it's possible. The value we get from the cosmic microwave background, the one that suggests a slower expansion,
Right.
that points to an older universe around 13.8 billion years old.
Right.
But the value from the local distance ladder measurements, the one suggesting a faster expansion,
Right.
that implies a slightly younger universe.
So we might need to adjust our cosmic calendar a bit.
It's possible.
Yeah.
And it's not just about getting the age right.
Oh, there's more.
Yeah, this Hubble tension, it also has implications for the fate of the universe.
Okay, now we're talking about the really big picture stuff. So what's the verdict? Eternal expansion or a big crunch?
Well, it's still an open question, but this Hubble tension definitely adds another layer of intrigue.
How so?
Well, if those local measurements are right, and the expansion is faster than we thought, That strengthens the case for eternal expansion, with galaxies just drifting farther and farther apart until they become isolated islands in this vast, cold, and dark cosmos.
So a rather lonely end for the universe.
It's one possibility, but if the CMB-based measurements are more accurate and the expansion is slower, well, that leaves open the possibility, though, a small one, of a big crunch, billions of years in the future.
So the fate of the universe is hanging in the balance, all because of this little discrepancy in the Hubble constant.
It's amazing how such a seemingly small detail can have such profound implications.
It really is. But it's not just about the age and the ultimate fate of the universe, right?
Right.
I remember the article mentioned something about the Hubble tension challenging our understanding of the fundamental laws of physics.
It does. Our current understanding of gravity and particle physics, the stuff that makes up the standard model of cosmology.
Yeah.
Well, it predicts a very specific value for the Hubble constant.
Okay.
The fact that our measurements don't match that prediction, it suggests that maybe, just maybe, there's something missing in our fundamental theories.
Whoa, are we saying that Einstein's theory of gravity might be wrong? Or that we need to completely rethink particle physics?
Well, it's too early to make such dramatic pronouncements.
Yeah.
But the Hubble tension definitely has theoretical physicists buzzing.
Yeah, I bet.
Some are proposing modifications to Einstein's general relativity.
Really?
Yeah, suggesting that gravity might behave a little differently at those mind-bogglingly vast cosmic scales or under the extreme conditions of the early universe.
So maybe gravity isn't as constant as we thought it was.
It's a possibility.
And then there are others exploring the possibility of new exotic particles or forces that could be influencing the expansion rate.
Exactly. There's a whole world of possibilities out there.
So this Hubble tension is really pushing us to re-examine some of the most fundamental concepts in physics.
It is. It's a challenge that's forcing us to rethink our assumptions and push the boundaries of our knowledge.
It's like we're trying to solve a puzzle, but we're missing a piece, and we need to figure out what that piece is and where it fits.
It's a great analogy for the scientific process.
What are some of the next steps in this cosmic quest, though? What kind of research or observations could really help us crack this case?
Well, one really exciting avenue is the development of completely new and independent ways to measure the Hubble constant.
Like what?
Well, for example, astronomers are now studying gravitational waves.
Gravitational waves?
Yeah, those ripples in space-time caused by cataclysmic events like black holes merging.
That's crazy.
It is. And those gravitational waves, they offer a totally unique way to measure cosmic distances, potentially bypassing some of the uncertainties we have with the traditional distance ladder methods.
So it's like having a brand new tool to explore the universe.
Exactly.
That's awesome. What else is on the horizon?
But we're also entering this golden age of telescopes, both on the ground and in space.
Wow.
And this new generation of telescopes, they're going to be able to provide even more precise measurements of the cosmic microwave background and those distant galaxies.
So we'll be able to peer even further back in time.
Exactly. And that'll help us refine our understanding of the early universe and how dark energy has evolved over time. Those observations will be crucial for solving the Hubble tension.
It's amazing to think that we live in a time where we have the technology and the knowledge to even tackle these fundamental questions about the universe.
It is a remarkable time to be a cosmologist.
It makes you realize how far we've come, but also how much we still have left to learn.
Absolutely. The universe is full of mysteries, and the Hubble tension is a prime example of how we're constantly pushing the boundaries of our understanding.
Well, this deep dive has been incredible.
Right.
We started with this seemingly simple question about how fast the universe is expanding.
Right.
And we ended up exploring the age, the fate, and even the fundamental laws that govern the cosmos.
It's been a real journey.
It really has. It's been a mind-bending exploration, and it's clear that the mystery of the Hubble tension is far from over.
It's a puzzle that will likely keep cosmologists busy for years to come.
To all our listeners out there, thank you for joining us on this deep dive. We leave you with this thought to ponder, what if this Hubble tension isn't a problem to be solved, but rather a window into a deeper understanding of the universe, one that challenges everything we thought we knew and forces us to expand our view of reality?
It's a tantalizing possibility.
It is. Until next time, keep exploring.